January 1942, Boeing Plant 2 in Seattle was supposed to be pumping out flying fortresses at a rate that would darken German skies. Instead, the factory floor looked like an industrial traffic jam. 63 B-17 bombers sat incomplete on the assembly line, each one representing a promise America couldn't keep. The Army Air Forces had ordered 3,615 bombers for delivery throughout the year. Boeing had delivered 9. General Henry Hap Arnold, commanding general of the Army Air Forces, wasn't just disappointed. He was furious. In a heated January 15th meeting with Boeing executives, Arnold made it brutally clear. Without bombers, there would be no strategic bombing campaign. Without a strategic bombing campaign, American soldiers would face an entrenched Nazi war machine for years. The math was simple and terrifying. The problem wasn't manpower. Boeing had hired over 30,000 workers in 6 months. Many of them women who'd never set foot in a factory before. It wasn't materials either. Aluminum was flowing in from Alcoa faster than they could use it. The crisis was something nobody had anticipated. The bombers themselves were too complex to build quickly. Each B-17G required 140,000 individual parts. Thowings alone demanded 12,000 rivets per side, connecting 7 overlapping layers of aluminum skin to an internal framework that had to withstand stresses of up to 6 Gs in combat maneuvers. Traditional assembly methods perfected in smaller aircraft simply collapsed under this complexity. Philip Johnson, Boeing's production manager, walked the factory floor every morning at 5 a.m., clipboard in hand, watching the same nightmare unfold. Wing Assembly Station Number 4 had 17 workers clustered around a single wing section. They were getting in each other's way. One riveter would finish a seam, step back, and another would need to access the exact spot he just vacated. Then a third worker needed that position for a different rivet line. The choreography was insane. Johnson timed it himself. 20 hours 14 minutes to complete one wing assembly from bare framework to final rivet. 20 hours. The British were losing bombers faster than that over Germany. Every Luftwaffe fighter that went unchallenged because American bombers weren't in the sky meant more merchant ships sunk in the Atlantic. More factories running at full capacity in the Ruhr Valley. More time for Nazi Germany to consolidate its grip on Europe. Boeing's engineers had already tried everything. They'd redesigned tool access points. They'd created specialized jigs and fixtures. They'd even experimented with different crew sizes, thinking maybe fewer workers would reduce congestion. Nothing worked. The fundamental problem remained. The rivet pattern specified in the engineering blueprints required work crews to access the same physical space in an overlapping sequence. You couldn't parallelize the work. You couldn't add more workers to speed it up. It was a bottleneck written into the aircraft's DNA. By late January, Boeing executives were having quiet conversations about the unthinkable, telling the Army they couldn't meet production targets. Some even whispered about bringing in Douglas or Consolidated to take over primary production. On January 28th, a classified memo circulated among senior management. The subject line read, Crisis Assessment B-17 Program Viability. Nobody wanted to be the person who lost the war because they couldn't figure out how to rivet aluminum fast enough. Walk into Wing Assembly Station 4 on any given morning, and you'd see what looked like organized chaos that wasn't actually organized. The wing section lay on a massive jig, a skeleton of aluminum ribs and spars spanning 32 F-7 layers of aluminum sheeting, each one precisely cut and drilled with thousands of holes waited to be attached in a specific sequence. The process started from the wing root where it would eventually bolt to the fuselage and worked outward toward the tip. Sounds straightforward. It wasn't. The engineering blueprint specified that rivets had to be installed in rows running parallel to the wing's leading edge. Row 1, then row 2, then row 3, marching backward toward the trailing edge. This pattern made perfect structural sense. Each row reinforced the one before it, creating an overlapping shingle effect that distributed stress loads across the wing surface. The engineers at Boeing's Developmental Center in Seattle had calculated every rivet's position to optimize strength-toe ratios. On paper, it was beautiful. On the factory floor, it was a disaster. Here's why. To install row 1, a riveter worked from the top surface while a bucker, the person who held the backing bar, worked from below through the wing's internal structure. They had to be perfectly synchronized. The riveter's pneumatic gun drove the rivet through pre-drilled holes at 3,000 lb of force. The bucker's bar pressed against the rivet's tail from the opposite side, shaped the molten aluminum into a mushroom head that locked the sheets together. Missed the timing by half a second and you got a loose rivet that had to be drilled out and replaced. That added 3 minutes per mistake. Multiply that across 12,000 rivets and mistakes became catastrophic. But the real nightmare started when row 2 began. To access row 2's rivet line, workers needed to position themselves exactly where row 1's crew had just been working. Except row 1 wasn't finished. Not completely. Quality inspectors needed to check every 10th rivet with a borescope, a tedious process that took 15 minutes per wing section. So row 2's crew waited and waited. Meanwhile, row 3's crew, already suited up and ready, stood around burning daylight. The production schedule called for parallel work streams, but the physical reality of the wing's geometry made that impossible. You simply couldn't fit enough workers around the structure to rivet multiple rows simultaneously. The rivet guns themselves created another problem. These weren't delicate precision instruments. They were industrial pneumatic hammers that shook your entire body when fired. The compressed air hoses snaked across the factory floor like demented pythons, constantly getting tangled with electrical lines for the inspection lights and tripping workers who were trying to move between stations. One riveter moving from position A to position B had to unplug his air hose, coil it up, walk around 3 other workers, find a new air coupling station, plug back in, and resume work. That 30-second process happened 70 times per wing section. Then there was the heat problem. Seattle in January wasn't warm, but the factory was. 17 workers clustered around one wing section, each one generating body heat, each pneumatic gun adding more warmth to the enclosed space. The aluminum sheeting absorbed that heat and expanded microscopically. Not much, just 0.03 in per 10T section. But when you're trying to align pre-drilled holes that have 0.2 intolerances, that expansion meant holes didn't line up. Riveters spent 15% of their time using tapered reamers, tone-large holes that had shrunk out of alignment as the metal cooled. None of this appeared in the engineering specifications because nobody had anticipated 17 people working in such close proximity for such extended periods. Frank Shamansky didn't look like someone who'd changed the course of the war. He was 31 years old, 5'7" with hands that were permanently stained with aluminum dust and cutting oil. Before Pearl Harbor, he'd worked at a Chrysler plant in Detroit, installing door panels in Windsor sedans. Repetitive work, mindless work. The kind of job where your hands knew what to do before your brain caught up. When Boeing started hiring in late 1941, Frank moved his wife and 2 daughters to Seattle, took a room in a boarding house near the plant, and joined the swing shift at Wing Assembly Station 4. He started work at 4:00 p.m. and finished at midnight. 5 days a week, sometimes 6 mo, when production quotas demanded it. What made Frank different wasn't his riveting skill. Dozens of workers could match his speed and precision. What made him different was that Frank couldn't stop watching the whole process. Most riveters focused on their immediate task. Line up the gun, squeeze the trigger, move to the next rivet, repeat 400 times per shift. Frank saw the entire ballet. He noticed that Jenkins, working row 3, was always waiting for Patterson to finish row 2. He noticed that Patterson was always waiting for quality control to clear row 1. He noticed that the sequence created a cascade of delays that compounded geometrically as you moved across the wing surface. On February 4th, during a midnight break, Frank sat on an overturned parts crate eating a bologna sandwich and staring at a completed wing section that was being moved to final assembly. Something about it bothered him. The rivet pattern looked perfect from a structural perspective. Each row overlapped the previous one, creating that shingle effect the engineers loved. But Frank kept thinking about his old job at Chrysler. When they installed door panels, they didn't start at one edge and work across. They started at 4 corners simultaneously and worked toward the center. Why? Because it let 4 workers operate in parallel without getting in each other's way. The geometry of the door panel made parallel work possible. He looked back at the wing schematic posted on the station's bulletin board. The rivet pattern ran in straight lines from leading edge to trailing edge, parallel rows marching across the wing surface. But the wing itself wasn't a flat rectangle. It was a complex 3-dimensional structure, with depth with internal ribs creating separate chambers with access points at specific locations. What if the rivet sequence matched the wing's actual geometry instead of treating it like a flat sheet? What if you started at multiple points simultaneously? Points chosen because they gave workers maximum physical access without overlap. Frank grabbed a pencil and started sketching on the back of his time card. Instead of straight rows, he drew a pattern that looked almost random. Rivets clustered around structural ribs where access was easiest. Then radiating lines connecting those clusters. following the natural contours of the wing's internal structure. It looked wrong. It looked like someone had spilled rivets on the blueprint and decided to leave them where they fell. But as Frank traced the pattern with his finger, he realized something crucial. You could have 5 workers riveting simultaneously without any of them needing the same physical space. Worker 1 could be at the wing root inside the main spar chamber. Worker 2 could be mid-wing accessing through the inspection panel. Worker 3 could work the trailing edge, which was shallow enough for top-down riveting without a bucker. They'd never intersect. The structural implications worried him. The engineering blueprint specified that parallel row pattern for a reason. Load distribution, stress concentration, terms Frank only half understood. But he kept thinking about something else he'd noticed. Rivet failures almost never happened where 2 rows met. They happened at transition points where the wing skin changed thickness or where cutouts for fuel tanks interrupted the pattern. The rows themselves weren't magical. They were just one way to distribute fasteners across the surface. Maybe not the only way. Frank knew what would happen if he walked up to a production supervisor with his sketch. They'd smile politely, tell him the engineers had spent months calculating those rivet positions, and send him back to his station. The hierarchy in Boeing Plant 2 was rigid. Engineers designed, supervisors managed, workers assembled. Nobody expected innovation from a guy whose job title was Riveter Grade 2. But Frank had one advantage. He worked swinging shift and swing shift. Supervisor Bill Hendricks was different. Hendricks had started as a sheet metal worker himself. Before being promoted to supervisor in 1940, he actually listened to floor workers, which made him either remarkably progressive or dangerously naive depending on who you asked. On February 11th, Frank caught Hendricks during the 8 RPM shift change and showed him the sketch. Hendricks stared at it for a long time. Then he said something Frank hadn't expected. "This violates every structural loading principle Boeing uses. You know that, right?" Frank nodded. He knew, or at least he suspected. Hendricks kept talking. "The parallel row pattern isn't arbitrary. When the wing flexes under load, stress concentrates along predictable lines. The rivet rows are positioned perpendicular to those stress lines. That's foundational stuff. It's in every aerospace engineering textbook published since 1927. The principle Hendricks was describing came from work done by Theodore von Karaman and his team at Caltech in the late 1920s. They'd proven mathematically that fastener patterns in load-bearing structures needed to follow stress trajectories. The invisible lines of force that flow through metal under pressure, a B-17 wing carrying 6,500 lb fuel, plus the structural weight of 4 engines experienced enormous bending stress during flight. The bottom surface was under tension trying to stretch. The top surface was under compression trying to compress. Right along the middle, the neutral axis stress approached 0. Von Karman's equations showed that fasteners needed to be densest where stress was highest and could be sparser where stress was minimal. The parallel row pattern achieved this perfectly. Each row corresponded to a specific stress magnitude with rivet spacing, calculated to match load requirements. Frank's pattern threw all of that out the window. His clusters placed dense rivet concentrations around structural ribs, not stress lines. His radiating connections followed access convenience, not load paths. From a classical engineering perspective, it was gibberish. The wing might hold together during taxi tests, might even survive the first few flights, but under sustained combat stress, microfractures would develop where the rivet pattern failed to match the stress pattern. Those fractures would propagate. The wing would fail. Men would die. Hendricks explained all of this to Frank in the noisy factory floor, shouting over the pneumatic guns. Then he asked a question that changed everything. But did Von Arman ever consider assembly efficiency as a structural factor? Frank looked confused. Hendricks continued. If it takes us 20 hours to rivet a wing and we make mistakes because workers are exhausted and cramped and tripping over each other, how many of those 12,000 rivets are actually installed to specification? How many are slightly loose because the bucker missed his timing? How many holes are slightly reamed because they didn't align perfectly? Your pattern might be theoretically weaker, but what if it produces practically stronger wings because the installation quality is perfect? This was heresy. Boeing's quality control processes assumed that workers followed procedures correctly. The procedures were designed around the engineering specifications. If wings were failing quality checks, you retrained workers or fired them and hired better ones. You didn't redesign the aircraft to accommodate worker limitations. That was backwards thinking. That was letting the tail wag the dog. But Hendricks had seen something in his 3 years as supervisor. He'd seen that theoretical perfection and practical reality diverged more than engineers wanted to admit. He'd seen riveters so exhausted by hour 18 of a wing assembly that their hands shook. He'd seen buckers miss their timing because they'd been crouched in the same position for 40 minutes and their legs cramped. He'd seen quality inspectors approve marginally loose rivets because rejecting them would mean another 2-hour delay, and production quotas were already impossible. What if Frank's impossible pattern, by reducing assembly time and worker fatigue, actually produced more reliably perfect installations? Ricks folded Frank's sketch and put it in his pocket. "I'll talk to someone," he said. Frank went back to his rivet gun, expecting nothing. Chris didn't go to the chief engineer. That would have been suicide. Oliver Eccles, Boeing's head of engineering for the B-17 program, had a reputation for eating floor supervisors who questioned his designs. Instead, Ricks went to Donald Douglas, no relation to the aircraft company, who was assistant production manager and who was also 3 weeks away from being fired if production numbers didn't improve. Douglas was desperate enough to listen to crazy ideas. On February 18th, Douglas looked at Frank's sketch for about 30 seconds before saying, "This is garbage. Get it out of my office." Chris didn't move. He pulled out his notebook and showed Douglas something else. Assembly time logs from Wing Station 4 over the past 6 weeks. Every single wing had taken between 19 and 22 hours. Not a single outlier. Not one crew that figured out how to go faster. The bottleneck was structural, built into the process itself. Douglas looked at the numbers, then back at the sketch. Even if this works from an efficiency standpoint, Eccles will never approve it. Never. He'd rather shut down the plant than rivet a wing in a non-standard pattern. Here's what Douglas understood that Ricks didn't. Boeing was weeks away from losing the B-7 contract entirely. Consolidated Aircraft had been lobbying the Army Air Forces hard, arguing that their B-24 Liberator was easier to manufacture and could be produced in higher numbers. General Arnold was listening. If Boeing couldn't demonstrate dramatic production improvements by March 15th, the Army would redirect orders to Consolidated and other manufacturers. Boeing would keep some production, but they'd lose their position as America's primary heavy bomber supplier. That meant layoffs. That meant Seattle's economy collapsing. That meant Douglas losing his job anyway. Douglas made a decision that violated about 17 different Boeing protocols. He authorized a test without engineering approval, but he couldn't do it during day shift when senior management was walking the floor. He couldn't do it on swing shift because too many people would see. He scheduled it for graveyard shift February 21st, starting at midnight. He pulled a wing section that had already failed quality control for unrelated reasons, a damage spar that made it unsuitable for flight. So if the test went catastrophically wrong, they weren't wasting a good wing. He assigned Frank and 4 other riveters, all swing shift veterans who'd volunteered, and he told absolutely nobody else. The test began at 12:14 a.m. Frank had spent 3 days refining his pattern, working out exactly which rivet clusters went where, calculating sequences that would let all 5 workers operate simultaneously. He'd color-coded the blueprint: red for worker 1, blue for worker 2, green for worker 3, yellow for worker 4, purple for worker 5. Each color represented a physical zone that didn't intersect with any other color zone. The workers could literally rivet at the same time without coordinating, without waiting, without bumping into each other. It looked insane watching it happen. Traditional riveting had a rhythm, a sequential logic. This looked like controlled chaos. One worker was inside the main spar cavity. Another was underneath the trailing edge. A third was working topside near the leading edge. They weren't following rows. They were following clusters, and those clusters seemed randomly scattered. Douglas stood 30 FT away with a stopwatch, chain-smoking Lucky Strikes. Chris stood next to him, silent. Every 15 minutes, Douglas checked his watch and wrote down the time. At the 2-hour mark, the wing should have been maybe 20% complete. It was 45% done. The workers started to realize something unusual was happening. They weren't waiting. Not for each other, not for inspectors, not for access. Every rivet position Frank had marked was genuinely accessible without interference. The pneumatic hoses weren't tangling because workers weren't crossing paths. The heat buildup was lower because they weren't clustered in one area. The aluminum wasn't expanding as much because 5 heat sources distributed across the wing. Surface created less concentrated thermal load than 17 sources in one spot. At 2:21 a.m., 127 minutes after starting, the final rivet was installed. Douglas clicked his stopwatch. He didn't say anything. He walked up to the wing and started inspecting rivets at random, pulling out his borescope and checking for proper mushroom formation. Chris held his breath. Frank stood there covered in aluminum dust, trying to read Douglas's face. Douglas inspected 30 rivets before he trusted his own eyes. Each one was perfect. The mushroom heads were uniform, properly seated with no gaps between the aluminum sheets. He called over Jimmy Chen, the graveyard shift quality inspector, without explaining what he was looking at. Chen grabbed his toolkit and started a full inspection protocol, the same one he'd run on 200 previous wings. He checked rivet spacing with calipers. He used a thickness gauge to verify the sheet metal compression. He tapped each rivet head with a small ball-peen hammer, listening for the solid thunk that indicated proper seating versus the hollow ping of a loose rivet. Minutes later, Chen looked up and said, "This passes. I don't know what crew did this, but it's clean work." Douglas told him how long it took. Chen thought he was joking. Then he thought the stopwatch was broken. Then Here checked his inspection because wings that rivet that fast shouldn't be this clean. There had to be mistakes, rushed work, something wrong. He found nothing. The wing was perfect. Better than perfect, actually. Chen had been inspecting B-17 wings since July 1941, and he kept a private log of defect rates that he never showed management. The average wing had 140 rivets that needed attention during quality control. Loose rivets, misaligned holes, installation errors. This wing had 1111, less than 1/10 the normal defect rate. But passing visual inspection didn't mean the wing would survive flight loads. The rivet pattern was still completely wrong from a structural engineering standpoint. Douglas knew they needed real testing, the kind that required equipment and authorization he didn't have. At 3:30 a.m., he made another unauthorized decision. He called the night crew at Boeing's structural test facility in Building 7 and told them to prepare for an emergency stress test. He didn't mention that the wing used an unapproved rivet pattern. He just said they needed rush testing on a wing section for production validation purposes. The test facility had equipment designed to simulate flight loads. A massive hydraulic press could apply up to 150,000 lbs of force to awing section, bending it upward and downward to replicate the stress of flight maneuvers. The standard B-17 qualification required wings to withstand loads equivalent to 6.2 times the aircraft's maximum weight without permanent deformation. That was the safety margin. Army Air Force's specification, R-1816B, established in March 1941, mandated this testing for any structural modification to production aircraft. Douglas was about to test a wing that violated R-1816B in every possible way, using a facility that wasn't authorized for non-standard testing at 4 a.m. when nobody was watching. They mounted the wing section in the test frame at 4:15 a.m. The hydraulic press engaged, applying upward pressure that bent the wingtip skyward. Douglas watched the strain gauges. At 1 G equivalent load, the wing flexed normally. At 3 G, still normal. At 6 G, the deflection matched specification exactly. At 6.2 G, the qualification threshold, the wing held. No creaking, no rivet popping, no stress fractures forming in the aluminum skin. Douglas told the operator to keep going. At 7 G, the wing was still structurally sound. At 8 G, individual rivets near the wing route started showing strain, but that was expected. The wing route carried the highest loads and was supposed to be the first failure point. At 8.4 G, 4 G, the test was terminated not because the wing failed, but because Douglas was terrified of breaking the test equipment. They released the hydraulic pressure. The wing returned to its neutral position with no permanent deformation. 0. A properly designed wing should show some microscopic permanent set after being loaded to 8.4 G. This wing didn't. It behaved like it had been stressed to maybe 5 G. Chen ran his inspection protocol again, checking every rivet that had been under maximum load. None had loosened. None showed evidence of microscopic slippage. The wing was somehow stronger than wings built to the standard pattern. Douglas stood there at 5:47 a.m. trying to understand what he was seeing. Frank's pattern had placed rivet clusters around the structural ribs, and those ribs were the primary load-bearing members of the wing. By concentrating fasteners where the structure was strongest, Frank had accidentally created a pattern that reinforced the wing's natural load paths instead of fighting against them. The radiating connections between clusters acted like secondary stress distributors, channeling loads away from weak points. It wasn't random. It was organic. It matched the way forces actually flowed through the structure, instead of the way engineers thought they should flow. By 6 a.m. on February 21st, Douglas knew he had to bring this to someone who could actually authorize full-scale implementation, not Eccles, who would kill it on principle. He went straight to James Murray, Boeing's vice president of operations, waking him up at his home in Laurelhurst. Murray arrived at the plant at 7:15 a.m., still in his weekend clothes, and demanded to see everything: the test data, the inspection reports, the time logs. He watched Douglas's hands shake as he explained what they'd done without authorization. Murray's face was unreadable. Then Murray asked the only question that mattered. Can we train 200 riveters to use this pattern by Monday? Douglas hadn't thought that far ahead. He'd been so focused on proving the concept worked that he hadn't considered scaling it. Murray was already doing the math. If one wing went from 20 hours to 2 hours, and Boeing had 42 wing assembly stations, that meant they could increase wing production by a factor of 10 without hiring a single additional worker. Wings were the bottleneck. Fuselages were assembling faster than they could be mated to wings. Tail sections were stacking up, waiting for completed aircraft. The entire production line was constrained by wing assembly speed. Fix that and everything else would flow. Murray made the call that morning over Eccles's screaming objections, over protests from the engineering department, over dire warnings from Boeing's legal team about liability if wings failed in combat. Murray ordered the new rivet pattern implemented across all production lines effective February 25, 1942. He gave Frank Shamansky a $40 a week raise, and the title production methods specialist. He gave Hicks a promotion to senior supervisor. He told Douglas his job was safe, and he told Yoles that if he didn't like it, he could explain to General Arnold why Boeing was still building 14 bombers a month. The results were staggering. In March 1942, Boeing Seattle delivered 47 B-17s. In April, 91. By June, they hit 186 aircraft. But the real explosion came in July when all 42 wing stations were fully converted to Frank's pattern, and workers had mastered the new sequence. July production 284 B-17s. August 319. September 362 bombers rolled off the production line in a single month. That was more than the entire 1941 annual production. The impact on the air war was immediate and devastating for the Luftwaffe. In October 1942, the 8th Air Force flew its first mission with over 100 bomber-shitting industrial targets in Lille, France. The Luftwaffe had been built to fight defensive battles against raids of 20 or 30 bombers. They could swarm those formations, pick off stragglers, make every mission costly enough to be unsustainable. But 100 bombers, the defensive fire from that many B-7s created overlapping fields of fire that made fighter attacks suicidal. German pilots called it the Wall of Lead. They'd lose 3 fighters to shoot down 1 bomber, and the Americans just kept coming. By January 1943, the 8th Air Force was flying missions with 300 bombers. By summer, 500. Each one of those aircraft represented 2 hours of riveting time instead of 20. Each one carried $4,000 lb of bombs deeper into Germany than Hitler thought possible. The Schweinfurt-Regensburg missions in August 1943, the raids that crippled German ball-bearing production, required 376 B-17s. Without Frank's pattern, Boeing wouldn't have built that many bombers total by August 1943. The entire strategic bombing campaign, the effort that drew German fighters away from the Eastern Front and forced the Luftwaffe into an unsustainable war of attrition, depended on Boeing's ability to flood the sky with flying fortresses. Boeing Seattle wasn't the only factory using Frank's pattern. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had all adopted variants of it. Combined production across all facilities hit 500 km heavy bombers in a single month. The Germans were producing 1,000 fighters monthly to counter them, but it didn't matter. You can't win an air war when the enemy builds bombers faster than you can shoot them down. Frank Shamansky never became famous. He received a War Production Board commendation in July 1943, a certificate signed by someone he'd never met, and it hung in his daughter's bedroom until she moved out in 1959. Boeing gave him that raise and the fancy title. But after the war ended, production methods specialist positions were quietly eliminated in the 1946 workforce reduction. Frank went back to Detroit, worked at Ford for 23 years, and died in 1971 without ever knowing that his rivet pattern had fundamentally changed how aircraft were manufactured. Because it did change everything, not immediately and not obviously, But the principle Frank stumbled onto became doctrine. In 1947, when Boeing began designing the B-47 Strat jet, their first swept-wing jet bomber, engineers didn't start with theoretical rivet patterns. They started by consulting with assembly line workers about access points and workflow. The B-47's wing used a pattern that looked chaotic on paper, but could be riveted by 6 workers simultaneously in 3 hours. Nobody called it the Shamansky method. Nobody knew there was a Shamansky. They just knew that matching rivet patterns to assembly reality, instead of pure structural theory, produced better aircraft faster. Douglas Aircraft applied the same principle to the DC-8 in the late 1950s. Lockheed used it for the C-130 Hercules. When Boeing designed the 707, their first commercial jetliner, the engineering team included assembly line supervisors in the initial design reviews. Revolutionary concept. Ask the people who will actually build the thing whether the design is buildable. The 707's fuselage panels used what Boeing internally called cluster riveting, which was Frank's pattern with a corporate name attached. It cut 707 fuselage assembly time by 60% compared to the Strat cruiser it replaced. Their legacy showed up in modern aerospace manufacturing philosophy. There is a principle called design for manufacturability, or DFM, that every aerospace engineer learns in school. Now it says that a design's elegance is measured not just by its performance but by how efficiently it can be built. The textbook example taught at MIT and Caltech and every aerospace engineering program in the world is B-17 wing riveting. How a theoretically optimal pattern proved inferior to a practically optimal pattern. How assembly time reduction improved quality instead of degrading it. Most students never learn about Frank. They learn about Boeing's innovative production methodology development program, as if it was a committee decision. Modern aircraft like the Boeing 787 take this even further. The 787's fuselage sections are joined with computer-designed fastener patterns that look random, but are optimized for robotic installation. Each pattern is generated by algorithms that consider structural loads, assembly access, thermal expansion, and 20 other variables simultaneously. Frank did the same thing in 1942 with a pencil and a time card. He just didn't have the math to prove why it worked. He had something better. He had pattern recognition developed from watching thousands of rivets get installed and noticing what slowed everyone down. That's the uncomfortable truth this story reveals. Frank wasn't smarter than Boeing's engineers. He wasn't better educated. He didn't understand von Neumann's stress equations or load path analysis. What he had was different knowledge. He knew how tired you get crouching in the same position for 40 minutes. He knew how pneumatic hoses tangle when workers cross paths. He knew that theoretical perfection executed poorly produces worse results than theoretical imperfection executed flawlessly. Boeing's engineers knew how to calculate stress. Frank knew how to actually build things. Both types of knowledge were essential. Only one type was valued. The aerospace industry eventually figured this out, but it took decades. Modern aircraft development uses integrated product teams where machinists and assemblers work alongside engineers from day one. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers had veto power over design decisions that would make manufacturing impossible. That's Frank's real legacy, not the specific rivet pattern, which is obsolete now in an era of automated fastening systems. The legacy is the idea that the person doing the work might understand the work better than the person who designed it. Revolutionary in 1942. Common sense now, except we keep forgetting it and having to relearn it. Every innovation cycle produces its own Frank Shamansky, someone who sees the obvious solution that experts are too educated to notice. The smart organizations listen. The rest keep riveting wings in 20 hours and wondering why they're losing.